Hello students, this is Dr. Siva Nagaraju from IARE. Today we are going to discuss delta modulation and adaptive delta modulation. So before this delta and adaptive delta, we are having a PCM, DPCM. So in PCM, that means the full form of PCM is pulse code modulation. In PCM, the incoming analog message signal is converted into a digital one. So that means in PCM, whatever the signal is coming, all the bits are encoded. So it is a wastage of transmission bandwidth. So to reduce the transmission bandwidth wastage, we are go for delta modulation. So delta modulation is another type of digital modulation. So coming to the topic, here we're having the course outcome. This topic delta modulation and adaptive delta modulation come in module 3. So the module 3 we're having covered by course outcome 3rd. So CO3, which defines illustrate the concept of pulse modulation schemes, demodulation, sampling, quantizing, and coding for obtaining of digital data. So in this module, we are going to learn what is sampling and what is quantizing and how to encode and how to get the digital data. So that's why in this module, already we discussed PCM, pulse code modulation, and DPCM. Now we are going to discuss the delta modulation and adaptive delta modulation. So the first one is delta modulation. So in PCM, transmits all the bits which are used to code a sample, hence signal rate and the transmission channel bandwidth are quite large in PCM. To overcome this problem, delta modulation is used. Why? Because in communication, channel bandwidth is very important. So that's why we are going to reduce the wastage of channel bandwidth. Okay, so that's why you go for DM. So what is the structure of PCM? Why it is wasted? So once we are going to see here, I am giving the continuous source and this is my sampler. So LPF is there, but I'll show you. The important one is quantizer, then the encoder, and final one we're having the digital. So in PCM, the continuous information is coming to the sampler. The sampler, which is going to sample all the continuous information, that means it is going to discrete in time domain, and thereafter we are going to apply this discrete time signal to the quantizer. Then the quantizer also convert this continuous amplitude into discrete amplitude. So the output of quantizer is a pure discrete form. That means in time domain and in amplitude domain, both are discrete. Then we are going to apply this discrete signal to the encoder. So here the encoding is done. Then after we are called as digital signal. But here the wastage is going on. Well, whatever the signal is coming, that is all is going to encode it. So it requires more transmission bandwidth. So it is not acceptable and efficient communication. So we are going to reduce this channel bandwidth by using delta modulation. So what was going on in delta modulation? In delta modulation, an incoming message signal is oversampled to purposely increase the correlation between adjacent samples of the signal. So oversample means here it is higher than the Nyquist rate. It is higher than the Nyquist rate. So you know that Fs is equal to 2Fm. That is a normal Nyquist rate. Greater than means Fs greater than 2Fm. So here the sampling frequency is greater than 2Fm. So this is my Nyquist rate. So whenever you increase the correlation between the adjacent samples, then we can estimate easily. The relation is increased, the correlation between samples are increased, then we can estimate from one sample to another sample easily. So that's why here in delta modulation we are going to oversample. And what the delta modulation virtue? The principal virtue of this delta modulation is its simplicity. It may be implemented by applying a sample version of the incoming message signal to the transmitter that consists of a comparator, quantizer, and accumulator connected together. So here, say quantizer also used, but what is the difference? Here it is a 1-bit quantizer. The delta modulator contains 1-bit quantizer. It means it can quantize 1 bit at a time. Okay, so that's why this is a very simple design. So working principle of delta modulation. So how this process is going? As we are going to discuss here, delta modulation process compares the present sample value to the previous sample value. Based on the difference, amplitude is going to increase or decrease by the step signal. So already we discussed that is it is a 1-bit quantizer. Means here it may be increased or decreased by the step signal. So if the amplitude is increased, then the step size increased by 1 step. That is plus delta. If you use a plus delta, bit 1 out generated. And if the amplitude is decreased, then the step size is reduced by 1 step. That is minus delta. And bit 0 is generated. That means it's having plus or minus delta. Plus or minus delta. Okay. So here the delta modulation compares the present sample value to the previous sample value. So why? Here our main virtue is oversample version. In delta modulation we use oversample. So oversample means here the correlation between adjacent samples are increased. So that's why here we are going to compare the present sample value to the previous sample value. So based on the difference amplitude, here we are going to increase or decrease by the step signal. Okay. Now how this conversion is done, or means how this analog signal is converted into digital one. So in DM, a staircase approximation is provided to the oversample version of the message signal. So this staircase approximation is try to track the analog signal. So whenever it tracks, then it is going to digitize. So here the staircase approximation is try to tracking. So it is increased by step by step, step by step. Okay, so the difference in PCM, the difference between the input signal and its approximation is quantized into only two levels, that is a plus or minus delta. So here plus delta is positive increment and minus delta is decrement of the step size. Why? My staircase approximation is trying to track the message signal. When it catches, up to catching, we are going to increase my step size. So the difference amount is decreases, I am going to decrease my step size. Okay. So it operates on the difference amount, the difference amplitude. So how much difference to present one to the previous one? Then the staircase is moving towards to the message signal based on the step size. So if the approximation falls below the input signal at any sampling above, it is increased by delta. If on the other hand the approximation lies above the signal, it is diminished by delta. So that means plus delta minus delta. So that's why it is a very simple design. So here we are going to denote the input signal is m of t. So m of t means it is a continuous time signal and it's a staircase approximation by mq of t, by mq of t. So here it shows. So here you can see this staircase approximation is provided. So this is my mq. So the mq of t trying to track the message signal. So this red line indicates the message signal. So here it is trying to increase the step size. So here this is my plus delta, here also plus delta, and this one is my plus delta. So that's why whenever the plus delta is coming, here 1, 1, 1, 1 is generated. Wait, 1 is going to generate it. So here also plus delta. So that's why 1 is coming. Then after the approximation is above the message signal. So again is going to track. That means come back to the message signal. That means the staircase approximation is always in touch with the message signal. So here the approximation is above the message signal. So that's why the decrement is required. So minus delta, again minus delta. So up to this one, all is 0, 0, 0 is coming. So here also minus delta. So 0 is coming. Then after, again it is going to increase. So here the main virtue of this delta modulation is it is increment or decrement by the step size. So you know the step size, that is the difference or a gap between the two present levels. So already we discussed how quantization is done and what are the types of quantizations, already discussed. Okay. So now we can see the transmitter and receiver of delta modulation. So in the above we are having shown that sample input. So sample input means this is the output of the sampler. So here sampler is not shown, but the output of the sampler taken as the input to this transmitter circuit. So that's why here sample input m of nts, but basically it is m of t. We are applying the m of t to the sampler, then it converts into m of nts. So m of nts indicates it is discrete in time version, but not in amplitude version. Already we discussed in PCM. Okay. So here we're having a comparator. So this one is a comparator. So the comparator which compares two signals. One is the input signal, sample input signal, and the second one is the approximation delayed, M2 of NTS minus TS, the delayed version of the approximation. And these two signals are compared, then generated E of NTS. This is error signal. This error signal is applied to the quantizer. So the output of the quantizer is the EQ of NTS. And again, another important block is that accumulator. So accumulator is a single delay element we are taken. So having the delay is TS seconds. So this delay element with the feedback path or simple loop we can call as accumulator. This total dashed box indicates the accumulator. And finally, this EQ of NTS is going to encode the required DM wave is produced. Okay, so this is my transmitter. And coming to the receiver, so here I'm using same accumulator whatever used in the transmitter. So the receiver which receives that DM wave, or we can exactly call as distorted DM wave. Why? The transmitter which transmits the signal into the channel, whenever the signal enters into the channel, noise will add up. So that's why we can call it as additive white Gaussian noise. So having the Gaussian distribution and is always additive with the signal. So my receiver receives the distorted DM wave, either DM or whatever it may be. The receiver which receives that distorted signal or distorted wave. So after receiving, it is going to decode. Why? The encoder is the last part of this transmitter. So here starts with the decoder. So after decoded, the signal which is going to apply to the accumulator. So here we are coming back into the message is in analog form. Okay. So here shows that E of NTS is equal to M of NTS minus MQ of NTS minus TS. So already we know that M of NTS is the input signal, input sample signal, and MQ of NTS minus TS, that is the delayed approximation, and EQ of NTS, that is the quantized signal. That means the output of the quantizer is equal to delta sigma function of E of NTS. So that means the quantizer contains a hot limiter which is going to increment or decrement delta. That means plus or minus delta is provided in the quantizer. And then the last one is MQ of NTS, the quantized message signal, that is equal to MQ of NTS minus TS plus EQ of NTS. So where TS is the sampling period. So E of NTS is an error signal representing the difference between the present sample value M of NTS of the input signal and the latest approximation to it. So it is M of NTS minus MQ of NTS minus TS. Already it's seen in the previous expression, E of NTS value. So EQ of NTS is a quantized version of the E of NTS. So the quantized output EQ of NTS is finally coded to produce the desired DM signal. So the comparator computes the difference between the two inputs. The quantizer consists of a hard limiter with an input-output characteristic that is a scale version of the signal function. And the accumulator operates on the quantizer output so as to produce an approximation to the message signal. Already we discussed earlierly, but that one in delta modulation, a staircase approximation is provided to the incoming message signal. So that's my approximation, my staircase approximation is ready to track the message signal. Further to tracking, it is going to increase delta or decrease delta. So that means delta means step size. Okay. So the quantizer output is then applied to an accumulator, producing result M2 of NTS, that is equal to delta sigma function of E of ITS, where I value changes from 1 to n. So it is a finite number. So the continuous signal is infinite. So from infinite to finite. So here I will discuss this one. If the input signal M of NTS is greater than the most recent approximation, that is M2 of NTS, a positive increment plus delta is applied to the approximation. So this is the increment, positive increment. On the other hand, the input signal is smaller, then I am going to negative decrement, that is minus delta is applied to the approximation. So now finally the receiver. So in the receiver, the staircase approximation M2 of T is reconstructed by passing the sequence of positive and negative pulses produced at the decoder output through an accumulator in a similar manner to that used in the transmitter. So the out of bound quantization noise in the high frequency staircase approximation were found. M2 of T rejected by passing H through a low pass filter with the bandwidth equal to the original message signal. So the receiver also contain the LPF, low pass filter. So out of band means beyond that our frequency ratio. So here the noises and DM system. So what are the noises is expected from this DM system? So delta modulation is subject to two types of errors. One is slope overload distortion and another is a granular noise. Another is a granular noise. So here you can see that M2 of NTS, which is equal to M2 of NTS minus TS plus E2 of NTS. Okay, so there is M2 of NTS is the digital equivalent of integration in the sense that it represents the accumulation of positive and negative increments of magnitude delta. Okay. So here you can see what is the slope overload and what is granular. So the staircase approximation is behind the message signal. So this case we can call as slope overload. So it is a try to tracking but not tracker. So that's why the difference between this approximation and the message signal, that gap we can call as slope overload distortion. So here my delta, my quantizer is trying to increase the step size. So that's why here plus delta, it is going to try plus delta, it is trying. So whenever it tracked, so that is the difference between the previous and the latest approximation, whatever it may be, that amount, the difference amount is going to apply. That is going to progress. So and the second one is granular. That means the staircase approximation is higher than the message signal. So then what to do? We are going to decrement. So my staircase is above the message signal. So I am going to decrease my step size. So that is minus delta. So here also the sampling time. Why? Because initially we discussed a delta modulation. Here we are going to oversample. Oversample version is used here. So that is the sampling frequency is greater than or equal to 2 FM. So here the condition what is required to avoid this slope overload, that is delta by Ts greater than equal to maximum slope of the message signal. Here m of t is message. So this is a maximum slope of the message signal. So this is a slope of the delta modulation system. So this is a condition to avoid the slope overload. Delta by Ts is greater than the maximum slope of the message signal. So we follow this condition to avoid the slope overload. Okay. So here we're taking a small problem, that is given a sine wave of frequency FM and amplitude A applied to a delta modulator having step size delta. Show that slope overload distortion will occur if A greater than delta by 2 FM Ts, where Ts is the sampling period. Okay, so here we are using the previous condition what we discussed. So that one is slope of delta modulator, that is a delta by Ts greater than or equal to maximum slope of the message signal. So this is the condition to avoid the slope overload. Okay, so this is the condition to avoid slope overload. So whenever the slope over distortion is arises, this message signal slope is greater than the slope of the delta modulator. At that situation we are having slope overload. So this is the avoiding condition. But when this overload is existing, so maximum slope of the message signal dm by dt is greater than delta by Ts. That is a reverse condition. The first one is for avoiding slope overload distortion. The second one is when the slope overload arises. Okay, so here what we're going to show, A is greater than delta by 2 FM Ts. So we are going to show this one. Okay, so here we know that m of t is nothing but message signal. So we can show it as a sine 2 pi fmt. Okay, so I am going to substitute this maximum slope d by dt a sine 2 pi fm t greater than delta by ts. So when you're going to derivative sine term, we got cos. So what I got, maximum value of a 2 pi fm cos 2 pi fm t greater than delta by ts. So here you can put outside this a sine a 2 pi fm, and the maximum value of cos is 1. So you got a 2 pi fm greater than delta by ts. So what it asking? A is greater than delta by 2 pi fm ts. So this is the required one for this problem. We have proved this one by using a simple condition. Okay. So the second situation is the staircase approximation mq of t to hunt around a relatively flat segment of m of t, so which is illustrated in the back end of the figure. Already we discussed in that figure. So granular noise in delta modulation may be viewed as the analog of quantization noise in pulse cone modulation. Okay. So what are the advantages of this delta system? So the advantage of delta modulation is the process of transmits only one bit, either 1 or 0 per one sample. So it requires lower channel bandwidth than the PCM. And the signal rate also small because it generates only one bit per one sample. So already we started with this comment. There is it requires lower channel bandwidth and lower the signaling rate. Okay. So this is the main advantage of this delta modulation. Now we will go for the adaptive delta modulation. So whatever the drawbacks is seen in that delta modulation, that is going to overcome in this adaptive delta. Whereas in delta modulation, we are having the limit. We can increase only one step. There is fixed step size. Here in delta modulation, having the fixed step size. But in adaptive delta modulation, we don't have such type of fix. Okay. So here it is ready to track the message signal. The staircase approximation is going to track the message signal. Okay. So here you can discuss adaptive delta modulation. So the performance of delta modulator can be improved significantly by making the step size of the modulator assume a time varying form. So in particular, during a steep segment of the input signal, the step size is increased. Conversely, when the input signal is varying slowly, the step size is going to reduce. Why? In delta modulation, we are going to use only plus or minus delta. That means if the message signal is increased like this, but we are going to step by step, like that. Why? It is a 1-bit quantizer. It can increase only 1 bit at a time, and it can increase one step at a time. So that is the problem. Why? This gap we can call as slope overload. I will discuss it. Okay. So in adaptive delta modulation, the step size of the staircase signal is not fixed and changes depending upon the input signal. So that is adaptiveness. That is my adaptive. Depending on the input signal, I am going to increase the step size of the staircase. Okay. Here first, the difference between the present sample value and previous approximation is calculated. This error is quantized. That is, if the present sample is smaller than the previous approximation, quantized value is high or else it is low. So there is adaptive delta. So here you can see. Here you can see the step size is not uniform. Is not fixed one. So it can increase according to the message signal. It depends on the message signal. Okay. So that increment is not there in delta modulation, ordinary delta modulation. But adaptive having such type of arrangement, it can increase their approximation depending on the message signal. Okay. So the output of the 1-bit quantizer is given to the logic step control circuit where the step size is decided. So the delta modulation doesn't having such type of arrangement. There is a logic step size control. So here we're having another arrangement when compared with ordinary delta. So this is logic for step size control. Whereas in a previous circuit, we are having only uh, 1-bit quantizer and accumulator and comparator, all such. But here, this one is the additional feature for this uh, transmitter, that is adaptive delta modulation. So the baseband signal X of NTS is given as input to the circuit. So the feedback circuit represents the transmitter as an integrator. The integrator generates a staircase approximation of the previous sample. So at the sum of circuit, the difference between the present sample value and staircase approximation of previous sample E of NT is calculated as usual in the delta modulation. So this error signal is passed to quantizer, where the quantizer value is generated, and the step size control block controls the step size of the next approximation based on either quantizer value is high or low. So the quantizer output given as output. Quantized signal is given as output. And this is my receiver. So here also what we use in the transmitter, that is a logic for step size control, is again used here. So as usual, what we discussed in the delta modulation receiver, so here also same. But another arrangement is that one, logic for step size control. And this input is given to the accumulator. So the accumulator, which produces the signal and passes through the low pass filter. The low pass filter having the signal frequency range is given. So if the beyond, if that bond exists other than the frequency range, it is just attenuates. So the low pass filter, which allows the low frequency signal and attenuates the high frequency. Okay. So why? Because the signal contain the noise. So generally noise can be treated as high frequency signal. So it is attenuated. Only the low frequency signal is nothing but message signal is passed to the. Okay. So here small description about this receiver. So the receiver has two parts. The first part is step size control. So here the receiver signal is passed to the logic step size control block, where the step size is produced from each incoming bit. The step size is decided based on the present and previous. And the second part in the receiver, the accumulator circuit recreates the staircase signal. This waveform is then applied to a low pass filter, which smoothens the waveform and recreates the original signal. Okay. So this is the working operation of the receiver of the adaptive delta modulation. So now what are the advantages of adaptive delta? So adaptive delta modulation decreases slope error present in delta. Already we've seen that. Why? Because these have adaptive nature. So based on the message signal, it can increase the step size. So slope overload is going to decrease. The slope overload error and granular present in delta modulation are solved using this modulation. Okay. So because of this, the signal to noise ratio of this modulation is better than the delta modulation. The dynamic range of adaptive delta modulation is large as the variable step size covers large range of values. Okay. So this is the advantage of adaptive delta modulation. Okay. So here the content of information is taken from Communications by Simon Hacking, 3rd edition. Okay. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.